Okay, this video is about properties of limits. So let's say that we have two functions f and g, and we know that as x is approaching c, we know that f of x approaches capital F, and as x approaches c, we know that g of x approaches capital G. So the assumption is that I know that these functions have limits, and I know what the limits are. And then if we want to consider what's happening to the function f of x plus f of g. So I'm adding, f of x plus g of x, and I'm adding these two functions, then it's pretty clear what's happening intuitively. This function is tending towards capital F, this function is tending towards capital G, and I'm adding them together. So the whole thing is going to tend towards capital F plus capital G. And the properties of limits in theorem 1.2 in your book, most of them are pretty straightforward, and this is very useful for calculating limits. So most of them are pretty straightforward. I want to say something at the end of the video just about number 4 is maybe the trickiest one. So they're very useful for calculating limits sometimes. Let's maybe look at an example. If I look at the function, if I look at the limit as t goes to infinity of, let's say, e to the negative t plus 1 over t plus 2 divided by let's say 3. Then I can use these properties. I know that the limit as t goes to infinity of e to the negative t is 0, because I'm taking e and raising it to a large negative number. And then I know that the limit as t goes to infinity of 1 over t is also 0, because I'm taking 1 and I'm dividing it by something tending to infinity, so dividing by a very large number. And then the other two are constants. So I know that I can use these limit properties. This is tending to 0, this is tending to 0, this is tending to 2 because it's always 2, and this is tending to 3 because it's always 3. And so this limit is just 2/3. Okay, now I want to be careful about property 4, so that's the division. So if I'm looking at the limit as x goes to some c of f of x over g of x, I need to be careful about this. So if this is, say, tending to 5 and this is, say, tending to 10, then yes, we can say that the limit is tending to 1/2. This is something close to 5, you divide by something close to 10, it's going to be very close to 1/2. This is going to be definitely okay as long as we're not tending towards 0 on the bottom. So if g is tending towards 0, then the point is that the function is tending towards something that might be undefined, right? And in this case, we just have to be careful. So I want to show you that anything can happen in this case. So if I look at, for example, the limit as x goes to 0 of, let's say, 7 times x divided by x squared, then this is sort of the same function. So this function is undefined at x equals 0, but everywhere else, it is the same exact function as if I cancel the x's, right? So at 0, both of these functions, actually these are the same function, because at 0, both of them are undefined, and everywhere else they take the same value. So these actually, 7x over x squared and 7 over x are exactly the same function. So this is the same limit. And so I can ask, what is this limit? Well, it's 7 and it's getting divided by something very close to 0. You can graph this thing. You'll see that kind of the graph of this function sort of looks like this. And so as x goes to 0, there's this vertical asymptote here. So this limit does not exist. So this limit does not exist. On the other hand, if I look at something like the limit as x goes to 0 of 7 times x squared over x, so I'm flipping the powers here, then this is actually the same function. Limit as x goes to 0 of 7x. These two are almost the same function. So 7x and 7x squared over x are the same function everywhere except 0, right? They output the same thing everywhere except 0. This one is defined at 0, but this one is not defined at 0. But since we're taking the limit near 0, it doesn't matter what happens at 0. And so these limits are the same. And now this limit, this function is continuous. I can graph it. And it goes through the origin. So of course, the limit as x approaches 0 is also going to be 0. So we have one that doesn't exist. We have one that goes to 0. And let me show you that we can have one that goes to anything we want. So now if I take the limit, sorry about that. If I take the limit as x goes to 0 of 7x over x, so now the top is tending towards 0, the bottom is tending towards 0, but this function is the same function as, well, let's graph this function, right? It's 7 everywhere. There's a hole at x equals 0, and it's 7 everywhere else. Right? So this is the same function as the limit as x goes to 0 of 7. These two functions, 7x over x and 7, are the same function everywhere except at 0. So I'm just not worried about this hole. And since it's the limit as x approaches 0, so it doesn't matter what happens at 0. So these are the same limits. And so this limit, of course, is 7, right? There's not even an x involved in this limit, so the limit is 7. And notice that the 7 could be any number, right? So in this example, the limit, it's going towards 0 on the top, it's going towards 0 on the bottom, but the limit is 7 or whatever the coefficient was, so it could be anything. In this first example, it was going towards 0 on the top, 0 on the bottom, but this limit did not exist. And here it was going towards 0 on the top and 0 on the bottom, but this limit was 0, actually. So if the denominator is tending towards 0, you have to be careful. Anything can happen.